What's up, guys? Welcome back to another recorded video. You might be asking, Jacob, how did we get from 3 to 6? The reality is that the numbering is based off the day that I showed this presentation, and some of the days were work days where there was no presentation to show for, which is why we are here at day 6. Now, just like day 3, we have another base sort of unit joke. This one is 6 in octal. Let me know in the comments if you get why this is funny. I'll continue on to the actual meat of this presentation. Today we're talking about communication buses. Who does not love a good communication bus? So the first thing, obviously, we got to talk about serial versus parallel. Serial communications is 1 bit at a time. You need some kind of encoding and decoding. Uses less wires and connections, but they're often slower. Granted, modern methods are more than fast enough. Parallel connections send multiple bits at the same time. They're simpler because you just run a bunch of different wires, but because there are a bunch of different wires, it takes up more space. You often get higher throughput. For example, on serial, you might take like 8 clock cycles to send a word, but if you have like 8 wires on parallel, you just use 1 clock cycle to send the whole word. In this, I will be talking about I2C or I2C, inter-integrated circuit, SPI or serial peripheral interface, universal synchronous asynchronous receiver transmitter or UART, or sometimes called USART depending on where you're reading this, and then CAN or controller area network. First one, I2C. This was developed in 1982. You have 2 main wires. I'm not including power and ground for this. You have SCL, which is the clock, and then SDA, which is data. Each client device has a different address, and then SCL and SDA have pull-up resistors that bring them up to the supply voltage, and lines are pulled to ground using a MOSFET. Only one device can receive or transmit data at a time, so this is half duplex. It is pretty simple and works for a lot of sort of sensors, but can struggle when it comes to a lot more higher data throughput where you might want to receive and transmit at the same time. This is an example of what a network might look like. Obviously here we have our pull-up resistors, we have our device that have their own resistors that they use whenever they're talking on SCL or receiving from SCL and talking on SDA. And then you can sort of just continue this. There is a limit to the number of devices that you can connect. That's pretty common for most of these protocols. The next one is SPI. This was designed and developed in the early 80s. Primarily, it's a 4-wire bus. There are 3 wires available, 3-wire versions that are available. We have chip select, serial clock, MOSI or master out slave in, and MISO master in slave out. Each additional peripheral needs its own chip select pin. Now this is full duplex because we have master out slave in and master in slave out. The chip select is often active low, so the device that is sort of in control of all of these other chips can choose which device it is talking to, which is pretty good as you can still get full duplex, and it's only 4 wires compared to I2C's 2, which isn't a ton extra, all things considered. Next one is UART. You probably have talked about this if you take it embedded design. It has an RX and a TX line, and they use shift registers to talk to each other. Now the issue is that because they use clocks, both devices must have the same clock speed and be synchronized. You can do this half duplex, but it's mainly used for full duplex communications, where you have sort of the transmit from one talking to the receive of a different chip in the shift register, have the clock going to both these shift registers as they shift data in or shift data out, and then this is where the chip actually can interact with the data. Now, this is the CAN standard. It was developed in 1984. it is very commonly used for cars. One of the main features of this is that you have high and low signals, and they're differential, and they are inverted from one another. The differential signaling improves the reliability of the bus because it is assumed if these two wires are next to each other, any noise will affect them both to roughly the same degree, and that change can be canceled out because it's the same in both. It is half duplex, which, depending on what you're doing, might be a bit of a downside. This is an example of a CAN frame. A frame is sort of what like one packet of a transmission might look like. Yeah. Let me know if you have any more questions, and I will do my best to answer. Hope to see you in the next video.